Dear students, in this video on magnetic effects of current, we will study about force on a current carrying conductor placed in a uniform magnetic field, force between two parallel current carrying conductors, and numerical problems based on them from your NCERT book. So let us begin with the first topic, that is force on a current carrying conductor placed in uniform magnetic field. So here we have shown uniform magnetic field B and a conductor AB which is carrying current I. Now you know that the electrons drift opposite to the current. As you can see, electrons move opposite to the direction of current with drift velocity Vd. And electron is a charged particle, so force experienced by each electron is given by minus E Vd cross B, the Lorentz force. And you know the Lorentz force is Q V cross B. Here charge on electron is minus E and velocity is Vd, drift velocity, and magnetic field is B. Now, all the electrons present in the conductor will experience this force. So if the number density of electrons is small n, and if the area of cross section is A here, and the length of the conductor is L from here to here, then the total volume of conductor will be area of cross section into length, and the electrons present in unit volume is n, so the total number of electrons present in the volume or in the conductor is NaL. So the total force experienced by all the electrons will be equal to the total force experienced by the conductor, and that is going to be this one. You see, multiply the force on one electron by NaL, right? And you know that NeAVD is given by the current. The relation between current and drift velocity is known to you, and then the relation modifies to this form. See, I is equal to NeAVD, and this minus sign is adjusted here. We can see that direction of current and direction of Vd, drift velocity, they are in opposite directions. So keeping that in mind, we can write F as I L cross B, or L is treated as a vector. You know that length is a scalar quantity, but here we are treating L as a vector quantity along the direction of the current, right? And now it's scalar form. So the scalar form is, you see, F is equal to ILB sine theta, where theta is the angle between the length vector and magnetic field. And the direction is given by the Maxwell's right hand screw rule. Direction is along the direction of the L cross B. So if you look at it, L cross B, and if the conductor and magnetic field are taken in the plane of the paper, then taking L cross B, the F will be directed outwards from this plane of the paper. So now let us take some special cases. When this theta is 0 or 180 degree, that means the conductor is placed parallel or anti-parallel to the magnetic field, and in that case force acting on it is going to be 0. So here we have taken a situation where the conductor is placed parallel to magnetic field. Current is parallel to magnetic field, so force experienced by it will be 0. Another case, here the conductor is carrying current in opposite direction. So in both the cases, in this case when current is parallel to B, in this case where current is anti-parallel to B, the force experienced by the conductor will be 0. Now, another very important thing, when theta is 90 degree, then you know that sine 90 is 1, which is the maximum value. So force experienced is ILB, maximum force. The force experienced by conductor is maximum when it is placed perpendicular to magnetic field. Now look at this situation. We have placed conductor L perpendicular to magnetic field B. It is carrying current I, and the force is shown by this direction. Now this force is maximum, as you can see, and this force is given by Fleming's left hand rule. Okay, where this current is shown by the your middle finger. So when you stretch your middle finger, index finger and thumb mutually perpendicular to each other, and if index finger is representing magnetic field and I is represented by middle finger, then your thumb will show the direction of magnetic field. And if you do so, then the force in this case is perpendicular or normal to this paper and directed inwards. You can try it and do it yourself. And what if the magnetic field is normal to the board? See, I have taken situation where magnetic field is normal to the board and directed inwards, and the conductor is placed in the plane of the paper. See, and it is carrying current like this one. So again, using Fleming's left hand rule, the force will be directed towards the left in the plane of the paper, as you can see. So you can extend your left hand mutually perpendicular to each other, thumb, middle finger, index finger, and you can find out the relation. Okay, force between two parallel infinitely long current carrying conductors. So here we have conductor PQ carrying current I1, RS carrying current I2 placed at distance R, and see, here this conductor PQ is carrying current I1, so it will produce magnetic field at this place, right? And it is producing magnetic field B1 everywhere, right? So we can assume that this RS is placed in uniform magnetic field B1. Now the value of this magnetic field is, you know this relation, this B1 is mu naught I1 upon 2 pi R. So this B1 is produced by PQ, right? Okay. Now this is normal to the plane of the paper inwards using your right hand rule. So if you hold this PQ in your right hand and extend your thumb along the direction of the current I1, then the sense of curling of your fingers gives the direction of B1. And according to this magnetic field is normal to the plane of the paper and directed inwards. Okay, so force acting on RS due to current I2. Now, just look at this one and forget about this one. So here we have a current carrying conductor carrying current I2 placed in uniform magnetic field B1. So it will experience a force. So force on its length L will be given by this relation, you see. So force on the second conductor F21 is equal to ILB. Now current in conductor is I2. Its length we have considered as L, and B1 is the magnetic field. And we can put the value of B1 from here, putting the value of B1 and just rearranging, you get mu naught I1 I2 L upon 2 pi R, right? Now this force is in the plane of paper directed towards PQ using your Fleming's left hand rule, right? Now magnetic field on PQ due to RS. See, exactly the same thing happened for this one also. This current carrying conductor will produce its magnetic field here. So the magnetic field on PQ due to RS, yeah, B2, you see, mu naught I2 upon 2 pi R. You can see that this magnetic field B2 is there, and it is produced at every point, you can see, right? And it is normal to the paper directed outwards using your right hand rule. And force acting on PQ due to current I1. Now current I1 is passing through it. This force will be directed towards the right side, and its magnitude will be same as this one. F21 is equal to F12, and putting the values, you see that you get the same value. So F12 is equal to F21. Okay. So the force per unit length. See, this force is acting on length L. This is also acting on length L. Then the force per unit length on both of them will be, divide the relation by L, and you get mu naught I1 I2 upon 2 pi r. Okay. So now what happens? See, if the currents are parallel, the forces are towards each other. That means they are attracting. These two conductors are attracting each other. And what if the currents are in opposite direction? If the currents are in opposite direction, they will repel. Like, see, this I1 will produce magnetic field directed inwards all the time. Okay. And because of this current I1 which is reversed, now the force will be towards the right, and because of this one, here also the magnetic field will be directed inwards, but the force will be directed away from it. So you have to learn to use your Fleming's left hand rule, and by using this, see, if the currents are in opposite directions, the conductors will repel. If they are along the same direction, they will attract. The definition of ampere from here. Very important. This is the definition of a fundamental unit or SI unit. You have done this definition in class 11th also. So you know that force per unit length is given by mu naught I1 I2 upon 2 pi r. And here, if the currents are taken as 1 ampere and the distance between the conductors is taken as 1 meter, and putting the value of mu naught, then the force per unit length becomes 2 into 10 raised to the power minus 7 Newton per meter. So from here we define this definition. So the 1 ampere is that current which, when passes through One ampere is that current which, when passes through each of two infinitely long parallel current carrying conductors placed 1 meter apart in vacuum, apply a force of 2 into 10 raised to the power minus 7 Newton per meter on each other. Okay, so this is the definition of fundamental unit ampere. And if you try to draw the magnetic fields around these conductors, if the currents are along the same direction, then you can see the magnetic field around it is anticlockwise, around this is this one, and if you look at the middle point, the magnetic fields are in opposite directions, they cancel out each other. So magnetic field at this point is 0. It is also called neutral point. And if the currents are in opposite direction, then at the middle point the magnetic fields will be added up. Magnetic field due to this one and magnetic field due to this one, they are adding up, and then the magnetic field here becomes double. So now let us move to numerical problem from your NCERT book. A long straight wire in a horizontal plane carries a current of 50 ampere in north to south direction. Give the magnitude and direction of B at a point P 2.5 meter east of the wire. So here you should be very clear about the directions. So I have placed the conductor along north-south direction, and if these are taken as north-south, then this is going to be east and west. And the problem is you have to find out magnetic field B at 2.5 meter east of the wire. So here the point is placed at 2.5 meter on the east side, right? So first it's important to understand the situation or problem. So the current given is 50 meter, distance is 2.5 meter, and magnetic field at distance r is given by this relation, mu naught I upon 2 pi r. You know the value of mu naught, 4 pi into 10 to the power minus 7. Current is 50 ampere upon 2 pi and r is 2.5 meter. So the magnetic field comes out to be 4 into 10 raised to the power minus 6 Tesla. Now we have to find out the direction of magnetic field also. So to find that out, we use the right hand rule. Right hand rule use karenge to, when this conductor is held in right hand with the extended thumb showing the direction of current, then the sense of curling the fingers gives the direction of magnetic field. So according to this B is normal to the plane of the paper and outwards. But you see that this is a horizontal plane. North, south, east, west directions are horizontal plane. So if this magnetic field is directed outwards, it means that it is directed vertically upwards. To try to visualize the situation. So this magnetic field is directed vertically upwards. Next problem, again unsolved problem from your NCERT book only. Okay, here. A 3 centimeter wire carrying current of 10 ampere is placed inside a solenoid perpendicular to its axis. And the magnetic field inside the solenoid is given by 0.27 Tesla. What is the magnetic force on the wire? So first try to draw the situation. When you whether diagrams are required or not, if you try to draw, you understand the problem. So here I have drawn a solenoid with magnetic field B, and this 3 centimeter wire is placed perpendicular to it, carrying current 10 ampere. Okay. So current length is 3 centimeter, current is 10 ampere, and magnetic field B is 0.27 Tesla. And you know this relation, F is equal to ILB sin theta. But here the angle between I and B or L and B is 90 degree. So sin 90 is 1, and putting all the values, see, I is 10 ampere, length L is 3 centimeter. Convert it to meters. So multiply by 10 to the power minus 2 into T, magnetic field B 0.27. Simplify it. You get 8.1 into 10 raised to the power minus 2 Newton. And direction of force is given by Fleming's left hand rule. Now the next problem. This again is your NCERT problem. Two long parallel straight wires A and B carrying currents 8 ampere and 5 ampere in the same direction are separated by a distance of 4 centimeter. Estimate the force on 10 centimeter section of wire A. Okay, so let this be wire A. Okay, so here we are given two long, that means we can treat them infinitely long straight wires carrying current I1 as 8 ampere, I2 as 5 ampere, and the distance between them is 4 centimeter, and the length on which we want to find out force is 10 centimeter. So the force per unit length experienced by the conductors. We know this relation, F upon L is equal to mu naught I1 I2 upon 2 pi R. This R is given to be 4 centimeter. So putting all the values here, the force, we can find out the force. We want to find out force on 10 centimeter. So take this L to the right hand side. You get this relation and put all the values here. Mu naught is 4 pi into 10 to the power minus 7. I1, I2, 8 ampere, 5 ampere. And the length is 10 centimeter. So 10 into 10 to the power minus 2. Centi means 10 to the power minus 2. You have to take everything in SI units. So upon 2 pi into R is 4 centimeter, 4 into 10 to the power minus 2. Simplify it, you get force F is equal to 2 into 10 raised to the power minus 5. See, the problems are not really difficult, but you must try to understand the situation. So read the question many times till you understand. So here, a straight horizontal conductor rod of length 0.45 meter and mass 60 gram is suspended by two vertical wires at its ends. A current of 5 ampere is set up in the rod through the wires. So I have tried to draw it here. We have a fixed rigid support and a rod here which is suspended using these two wires. The length of the conductor is given to be 0.45 meter and the mass of the wire is given to be 60 gram. So its weight will act downwards, and because of this there will be tension in the wires. Now the question is, what magnetic field should be set up normal to the conductor in order that the tension in the wire is 0? So here, if there is no magnetic field, this tension T plus T will be equal to the weight of the wire, balancing the forces. But what we want is, we want to make this tension 0. That means the force due to magnetic field should be acting vertically upwards. So this force due to magnetic field should be equal to mg. So the first part, force due to magnetic field balances the weight of the conductor, and according to Fleming's left hand rule, B should be perpendicular to the conductor directed inwards. Fleming's left hand rule, again you have to use it again and again, so be clear about it. So this force should be equal to mg. Put the value of m, that is 60 gram is 0.06 kilogram into g is 9.8, and you get this relation 0.059 Newton. So this force is known to us. Now we want to find out the magnetic field. So magnetic field, you see, ILB is equal to ILB is equal to mg. So I want B, so bring this IL to the denominator. So B is equal to mg upon IL. Put the values here. Put the values of mg and all that. We have found out mg already, and I is 5 ampere and L is 0.45 meter, and you get 0.26 Tesla. Now comes the second part of the problem. What will be the total tension in the wire if the direction of current is reversed, keeping its magnetic field same? Now if the direction of current is reversed like this, then the force which is upwards will also come downwards. When the current is reversed, F will act downwards, and in that case this F and mg will be added up, and the tensions will be sum of these two, right? That means force and mg are equal, so that means the tension will be twice of this force. So we get T is 2 into 0.59 Newton. that is 1.18 Newton. So even though the question looks little complicated, but it is a very simple problem. Another NCERT problem. See, all these problems are asked in your board examination also. This is also a very interesting problem. A uniform magnetic field of 1.5 Tesla exists in a cylindrical region of radius 10 centimeter. Its direction is parallel to axis along east to west. Okay, so here try to draw everything that is given to you. Here we have a solenoid which is cylindrical region, and I have shown the directions east, west, north, south here, east, west, north, south, and the magnetic field is from east to west as shown here. Magnetic field is from east to west. Now a wire carrying current 7 ampere in the north to south direction. I have a wire, see this is a wire I have shown here. I have shown this wire from north to south direction. The current is from north to south direction, right? And then the wire passes through this region. What is the magnitude and direction of the force on the wire if the wire intersects the axis? Now wire intersects the axis means that the wire is placed along the diameter of this cylindrical region, or you can imagine a solenoid kind of situation. So the magnetic field is perpendicular to the length of the conductor. Now again, this magnetic field will be perpendicular to the length of the conductor and force on the length enclosed in the solenoid. Now see, the cylinder will enclose its length equal to its diameter, right? So the F is equal to ILB sine theta. I is 7 ampere and L, see here, the radius of this cylinder is given to be 10 centimeter. So the length enclosed inside the cylinder will be 20 centimeter, right? Which is equal to 0.2 meter, and B is given to be 1.5 Tesla. So multiplying all this, we get F is equal to 2.1 Newton. If I try to draw this section, then the normal cross section, then the wire is placed like this, you see, and the magnetic field is say inwards, and the maximum, the length enclosed will be equal to the diameter of the cylinder, and magnetic field and the currents are perpendicular. So now just imagine the situation and use your Fleming's left hand rule. Now this force will be vertically downwards. See, remember that east, west, north, south, they all are in horizontal plane. Okay. Now comes the next problem. Part B. The wire is turned from north-south to northeast-northwest direction. Now again, just try to imagine the situation. Here, the initial position of the wire was this one, and magnetic field is directed normal to this plane. Now the wire is turned like this. Okay, and see, look at this situation now. Northeast northwest means this angle is 45 degree. Okay, so, and this is 10 centimeter as you can see, radius, right? So now the angle between magnetic field and L is 45 degree, but now the L which is used here has changed. It is basically a sideway view. If I try to show it, say this way, say this is your diameter, and now it is turned like this. The magnetic field is along this direction, this angle is 45 degree, and now a longer section of the conductor is inside the tube or inside the solenoid, you see. So to find, I'll draw it again for you. Initially it was placed along the diameter and the magnetic field is along this direction, and now it is placed like this. So this is 10 centimeter, this angle is 45 degree. We can find out this section, this length. Now this length will be equal to, if you write formula of sine 45, then you will get perpendicular upon hypotenuse, or the hypotenuse will be equal to length upon sine 45. Okay. So here the length enclosed will becomes the length upon sine 45. Now I is 7, L is 20 centimeter divided by sine 45. It is 0.2 meter upon sine 45, and B 1.5 Tesla, and sine theta sine 45. Now the angle between magnetic field and the length is 45 degree. So sine 45 cancelled. You are left with 2.1 Newton only, and this also will be directed downwards only using Fleming's left hand rule, using direction right hand screw rule also. And now comes the third part. The wire in north-south direction is lowered from the axis by a distance of 6 centimeter. So we have shown the cross section here. See, this cross section is shown from this side. So this is the cross section of the cylinder, and initially the wire was placed along this diameter. Now it is lowered by 6 centimeter. इसको 6 centimeter नीचे उतार दिया. तो अब हमें ये देखना है कि इस वायर के अंदर कितनी लेंथ इनक्लोज्ड है. Okay, so you can see that the radius, this radius is 10 centimeter. This vertical height is 6, and using your Pythagoras theorem, this smaller one will come out to be 8 centimeter. So the total distance, your total length enclosed will be 16 centimeter. So it is the same relation, but in place of L, we will use 16 centimeter. So here the length enclosed is 16 centimeter. Formula, and angle between B and L is 90 degree only. So F is equal to ILB. So putting the value of current, and the length 0.16 meter, B is 1.5 Tesla, simplify it, 1.68 Newton, and direction is vertically downwards. So you see that the problem is not difficult, only you should be able to visualize it and you should be able to solve it. So always try to draw diagrams so that you can understand. So I hope that this video is useful to all of you. Thank you for watching it.